Hello everyone, my name is Hamid Kayhani from Facebook. I hope everyone is remaining safe and healthy during this challenging time. It was unfortunate that we couldn't meet in person during the OCP Global Summit, but thanks to the OCP leadership, we can meet virtually during this virtual OCP Summit to exchange ideas and share information together. This is my pleasure to introduce this talk entitled Overview of OpenRAG v3 Power System. There has been a tremendous amount of effort and collaboration between Facebook and Microsoft and several other suppliers to bring this concept and solution from the ground up, writing the spec, going through the designs, and do the manufacturing and prototyping up to this stage. Myself, Tiffany Jean, Sean Harris, and Banya Sok, and several others have been contributed on this work, and I really appreciate their effort. Several new features has been designed for the OpenRAG v3 power system. The main ones are listed here. It's going to be one power zone with 48 volt output voltage. The power system and battery system are flexible and modular. You can add as much as power and backup as you want, basically add more power shelves or add more battery shelves, and you can place them anywhere in the rack. The power system and battery system are completely independent, so it gives higher reliability. It also gives you the option that don't use the battery if you don't want. The other important feature is the design of the new universal 7-pin AC power input connector that allows the power system to work with different voltage configuration, star, Y, 208, 240, and so on. 7 new components have been designed for the OpenRAG v3 power. There are 3 variants of the power shelves. There is a standard 48 volt rectifier module with 48 volt output and 3 kilowatt power. There is a power shelf management controller for communication purposes. 2 connectors have also been designed: output bus bar connector for power shelf and battery shelf, and 7-pin input connector for the power shelf input. There are also independent battery shelf as well as regulated battery backup module. Tiffany, our mechanical lead, is going to go through the mechanical area. Thank you.
Thanks, Hamid. Hi everyone, my name's Tiffany and I'm a mechanical engineer with Facebook. Let's take a look at the ORV3 rack, which has been discussed in more detail in previous sessions. This rendering shows the rear side of the rack with a central 48 volt bus bar in the middle. Power comes in from the data center through the top of the rack. The AC input cable is routed down the sides of the rack and can plug into the left and or right sides of the power shelf. The 1OU power shelf is shown in this picture, but we will go into details about the different power shelf and cabling configurations in later slides. Banya will later talk about the power shelf options in more detail. But in summary, we have 2 1OU options and a 2OU option as well. In the front of the 1U power shelf shown here, we have 6 rectifiers, or power supplies. And on the left side, we have a power shelf management controller, or PMC. The rectifiers and PMC modules are front serviceable and toolless, easily swappable in case of a failure. The 2 1OU options have either 1 or 2 AC inputs, bringing power into the shelf. This AC input connector is an OCP standard, the Universal Power Shelf Input Connector, which I will show in more detail in a later slide. The 48-volt DC output connector shown in the middle of the rear side of the power shelf interfaces toollessly with the bus bar in the rear of the rack and can power the entire rack of IT gear. This output connector is also an OCP standard, and we'll take a brief look at this as well. A 2U shelf option is also available. In the front of the system, there are 12 rectifiers instead of 6, and on the left side there is a PMC. You'll want to note that the rectifier and PMC modules are identical between the 1OU and 2OU shelves. In the rear of the system, there are two large input connectors used for the AC in, which can accommodate higher power up to 60 amps. The shelf is also recessed a bit more in the rear to accommodate this AC input connector size and cable bend radius. The DC output connector, which clips onto the bus bar, is also identical between the 1U and 2U shelves. The only difference is that there are two such clips on the 2OU instead of just one. This is the Universal Power Shelf Input Connector, which we showed in the previous slide with the 1U shelf. It is a 7-pin connector which is configurable as star, delta, or single phase. Each can accommodate up to 32 amps. The latching mechanism on the input cable is also toolless, and the connectors are keyed to prevent inappropriate assembly or any other issues. This is the high power AC input connector that was shown on the 2U shelf option. It is a 7-pin connector, which is configurable as star, delta, or single phase. Each of these can accommodate up to 60 amps. Finally, this connector is another new OCP standard. It is the DC output connector to be assembled on the rear side of both power shelves and the battery backup shelf. This is a floating connector with 3 mm float in both directions. The float is required because it blind mates to the bus bar. Contrast this with ORV2, which had fixed power shelves in fixed locations and was required to be bolted to the bus bar. This connector allows the flexibility of placing power and battery shelves at any location in the rack, and also allows for the flexibility of adding more power or battery shelves as needed. This connector is rated for up to 500 amps. Next, I'll hand it off to Banya, who will talk about the 48-volt rectifier in more detail.
Hey guys, how's it going there? You know, it's a shame that we all could not meet at OCP in March. I was really hoping that we could have had this conference, but you got to do what you got to do, right? With this coronavirus outbreak going on. I really hope everyone is staying safe and healthy. You know, wash your hands, practice social distancing, and quarantine if your state has that rule. Let me give a brief introduction about myself. My name is Banya. I'm the power engineer for Microsoft. I've been working on this PowerShell for the past years now. So today we had split up the slide deck here into 3 sections. Tiffany just had talked about her section on the mechanical part of the PowerShell and the power supplies and all that. I will do my portion now, and it starts from slide 12 to 16. So if you guys can just go to those ones, and I'll get started. All right, so hope everyone's on slide 12. Okay, so 3 kilowatt 48-volt rectifier. Okay, before I get started there, I just want to give my little rant. Rectifier. That's a term that we use in telecom business. It's derived from the 48 volts that got rectified from the AC. Now, myself personally, it's a big pet peeve of mine. I don't like to use that term. I would prefer to go with PSU. That's what I grew up with. So for the rest of my slides, I will refer to it as a PSU rather than a rectifier. So input for our power supply, it's going to be your standard 200 volts to 277. Obviously, we have 208, and that's derived from the 4 wires, for the delta connection, 208, 120. We have 240, that's derived from the 415 transformer. And then we have the 480, which you get the 277. So that's all standard normal stuff. We will be outputting 50 volts instead of 48 volts. Hamid will get to that part later. This is going to be a very narrow band. And the reason why is that when you go downstream to the DC-DC portion, you can use an unregulated DC bus for high efficiency gains. We currently plan to have 97.5% efficient. Well, I wouldn't say plan. We do meet 97.5% efficient, and that is included with the fans. At full load, obviously, it's going to be slightly less, and we have 96.5% right now. At the output side, we plan to use active current sharing for the tightness of the spec. However, when you have transient dynamic loading, I believe this will be going to voltage droop sharing mode. And obviously, it would be a lot better. The control loop needs to be worked on much harder if you want to have active current sharing only. Especially with 12 power supplies, it's going to be a little bit of a challenge. So we decided that we need to have both implemented. The power supply will communicate to a PMC, which stands for Power Management Controller, and that is the brain of the shelf. I will get to that section later in a bit here in slide 16, but let's go to the next slide. So in this slide 13 and 14, it's very similar. This is a 1 OU power shelf. It has 6 power supplies only, and it's 18 kilowatt N power. In this first option that I show here, you have 15 kilowatt N plus 1. It only has one AC input, so it's what will power the power supply, I guess. Let's go to the next slide. This one here is the only difference would be you have 2 whips coming in. So 3 power supplies will get 1 whip, while the other 3 would get the other one. Again, not much of a difference from the one before. It depends on the data center configurations, how the DC folks want to configure their power rack and shelf. And then we get to the third option. Now, I just want to say that this slide deck was done around the end of February. It was before the conference, obviously. And from then until now, there's been a few changes. I'd say if you want to know more about these changes, please contact us directly. Basically, the plan is to add another U so that you can do AC whips. It's off topic, so I won't get to it in this presentation. So for the option 3, we have 2 OU shelf, and now you're increasing your power from 18N to 36N, or you can do an 18N plus N or 35N plus 1. Everything else remains the same. So let me get on to the power management controller. As I said before, this is the brain of the power shelf. You have the PMC per either power shelf or battery shelf. The PMC is able to do health telemetry of the power supplies, do firmware updates command, and last but not least is to do power throttling or capping policy. Now, all of this can be done through the use of RS-485, Ethernet, and GPIO signals. We will have 4 RJ45 ports in front of the PMC to do this. Well, I believe that's it for my section. And now off we go to Hamid's slides. Thank you, everyone. I hope to see more of you guys involved with this project. Now, I did actually have a great analogy that I wanted to use, but I feel like when we do have our next face-to-face conference, I will talk more about this analogy. All right, you have a good day, everyone.
Thank you, Banya. Hey, this is Hamid back. Another important piece of this project is a battery backup system. We are planning to design an independent battery system to have higher reliability. Basically, the battery system doesn't rely on the power shelf to operate. It runs completely independent. In terms of power, the battery shelf will match the power shelf with 15 kilowatt output power with N+1 redundancy. We are targeting the design of a 3 to 5 minute end of life backup time in 2 OU shelf. Our design is basically going to be a regulated battery system with DC to DC converter after the battery, which gives several benefits. First of all, batteries share current equally and age similarly. It also allows mixing old and new batteries with different charge levels on the same rack. On the side, it also helps with the transient peak power shaving. The other benefit of having the fixed 48 volt output voltage is that it gives more efficient power system with a narrow range 48 volt concept that I will explain later. Here you can see some rack power configs based on the solution we presented. As we said before, the solution is completely flexible, so any customer can configure it in the way that meets their demand the best. The picture on the far left shows a rack with only one U shelf. It gives you 15 kilowatt at N+1. There is no battery backup if you don't want to. The second picture shows a rack with a power shelf and battery shelf. So it's 1U power shelf and battery shelf. You can get 15 kilowatt at N+1 and you have a backup time as well. The position of the power shelf or battery shelf can be anywhere in the rack. The picture on the third picture basically shows the power shelf and the battery shelf both in the middle. And again, you can get 15 kilowatt with N+1. The power cord, it could come from both either top or bottom. The fourth picture shows a 2U shelf. You can get 18 kilowatt at N plus N without any, there is no battery backup, so you won't have a battery backup in case you have an inline UPS or other approach. These are just a few examples, and customers can configure it in any other way that they prefer. Okay, now I'm going to explain how the system operates. On previous OpenRAC V2, the voltage range is 40 to 60 volt with a 54.5 as a nominal. We heard a lot of complaints from different folks that this range is too wide. The voltage can go up to 60 volt, which basically means we cannot use 60 volt components. We have to go with 100 volts. On the other side, the voltage can go down to 40 volts, which basically is an area with a very high currents. So the efficiency drops while there's a lot of challenge in the design. So the approach we came up with is basically adding a DC to DC converter after the battery pack that I explained before. That's the only additional component. In this approach, we basically regulate the rectifier to 50 volt fixed and the battery to 48 volt fixed. And there are two O-ring ideal diodes O-ring FETs on the design as well. So basically, when the AC voltage is available, the voltage on the bus is 50 volt, and when the AC is out or there's a rectifier failure, it actually goes to the battery with the 48 volt output. Minimizing voltage range on this narrow range 48 volt concept significantly reduce component size on both voltage and current ratings. So basically, you don't have to design and choose component to meet the high voltage area of 60 volt and high current area of 40 volt. On IT gears, this approach enables the use of efficient 4-to-1 fixed ratio converters, followed by conventional 12 volt point of load converters. On the OpenRAC V2 unregulated 48 volt approach, the voltage after the 4-to-1 fixed ratio converter is 10 to 15, in which most of conventional 12 volt converters doesn't work. And a very important piece of this approach is that the power flows naturally. So basically, you don't need to have any software control to command the different components. It's just the power flows naturally. It gives you more dependency and reliability. On the previous approach with an unregulated wide range 48 volt, you have to control the battery to disconnect or turn on some batteries that they don't share current, etc. Last but not least is that this solution makes the rectifier design very simple and therefore higher reliable and more efficient. The first draft of specs and prototype systems are ready. I'd like to ask everybody to review and provide us with feedback. I also encourage all the potential end customers and suppliers to join this effort. We like to have a common power and rack solutions that works for everybody. There will be several related topics today that I encourage you to attend. There would be a deep dive on the power systems with the three main suppliers. Steve, I, and Caleb will host a meeting to answer any questions that you might have on OpenRAC V3. And Tony from Facebook has done a good survey on 48 volt to 12 volt solutions. I encourage you to tune to that as well. There would be another dedicated presentation on the 7-pin connector from two main suppliers. Okay, so for the closing, I like to mention we didn't the goal of this project was not only to have a common rack and power system. It's basically preparing a platform that later on it allows different companies to exchange their IT gears, servers, storage, AI solutions. So I keep encouraging and asking everybody to contact us and join this effort. Thank you so much for listening to us, and we will be open to questions.
Hi everyone.
Hello,
I think
everyone.
Vanya, Hamid, and I are all here so that we can answer some of the questions live.
Yeah, hello everyone. This is Hamid here. Thank you for joining the call. We can go ahead with the question on the Q&A, and later on we go with the chat questions as well. So the first question is, are the power rectifiers pulling 48 volt for cooling fans and internal component as well? The answer is yes. They use 48 volts, the output of the power rectifiers or PSUs are 48 volts, so they use the 48 volt for any fans or any other systems. There wouldn't be any 12 volt. The second question from Brian Costello: how does the large connector for the 2OU fit through the rack side wall? Tiffany, can you respond that?
Sure. So for the 1OU, the connectors will fit through the rack sidewalls, but the 2OU connector is pretty large, so it will not go through the sidewalls. They're just going to go straight up from the back and not go through the sidewalls.
Thank you. Vanya, if you cannot talk, please join through the phone bridge. I think this is the way that we can go live and answer the question.
Can you guys hear me?
Yes.
Yep.
Now we can hear you.
Oh man.
Okay. So
All
now
right.
you're here. We will address the next question to you. How do you select between a star, delta, or single phase? I think this is for the connector, 7-pin connector.
Basically, you do not have to do any selection. We employ the universal whip. So all you have to do, you buy the correct whip for whichever configuration that your data center or your customer needs.
So this is like basically the factory. At the factory, they can configure it to the way that they want.
Exactly.
And then we use for the end application.
Mm-hmm.
One question actually in this one, and someone asked, is it possible that they reconfigure the connector in the data center floor, or should it be only at the factory?
Well, generally, it depends on the data center, right? I know Microsoft, we generally in the past, we had some sites that have the Delta configurations. And, nowadays on all our new data center, we don't use Delta anymore. We only build with Y configurations. But the thing is, we have to support both configurations. You can't just stop supporting Delta. So what we have done is use the universal connector. It has 7 pins. So depending on the data center, they can just buy the whip that would have one end use the Delta or or the N using Y, right? And the other N will be the same. It's always the universal, and that would plug into the PowerShell.
All right, thank you. Next question from Mark Lerner. What about ATS in PSU? We haven't designed to have ATS on the PSU. You could think about it just each PSU can get one input. And if you want to have more redundancy, you can have 2 feeds, like one of the options. It can have 2 feeds and half of the rectifier power from one feed and the other PSU rectifier power from the second feed. The next question from Mark Lerner: is PMC required? I think the question is that is PMC required for the power system to operation or for communication? Maybe Banya, you can answer that.
What's the question?
Is PMC required?
Oh, PMC is not required. That will depend on your, if you want to have some sort of management, the ability to read the telemetry of the power supply status and send it back, then yeah, you should definitely have it. Otherwise, it will work. It will provide power to your downstream equipment in the rack.
Okay. Maybe we can take one more question from John Laban. Are the new racks black? Tiffany.
Are the new racks black?
Yeah.
As far as I know, they're black currently. Although I think if you choose to go with RV3 and you want it a different color, you could have your own part number and handle it that way.
All right. I'm not sure if we can continue, but people will miss the next presentation. So I'm going to end this call. There would be another call in the, for the OpenRAC V3 questions. So feel free to come there, and the whole session will be open for questions. Thank you so much, everybody, for joining, and have a good rest of the day.
Stay safe.